Okay, so here we are. We've now gotten to the point where we've derived the number of modes per unit wavelength per unit volume. Okay, now we want to get the energy per unit wavelength per unit volume. Okay, and so we just have to assign an average energy per mode. Okay, so what Rayleigh and Jeans did is they used classical thermodynamic theory, and they said an equipartition theorem, which says that if you have a system with multiple modes, with many different modes, that the average energy per mode is just K, the Boltzmann constant, okay, times the temperature. Okay, so with that, then the average energy per unit wavelength per unit volume, okay, which we can represent as du d lambda. Now, du is the energy density, or U is the energy density. Okay, so that's the energy per unit volume, and this is equal to just 1 over a cubed times the energy per unit wavelength. Okay, so that's just notation, and then what we get is that again, if we assign the average energy of each mode, the average energy of each mode as kT, and this is just 8 pi kT divided by lambda to the fourth, because basically we've done all the work over here. We just have to assign, for each one of these modes, we just have to assign an average energy kT. Okay. Now, the thing that is that we would note here, so let's just first take stock of what we have here. This is the energy density per unit wavelength. So this is the should be related. This is the energy density in the cavity per unit wavelength. This should somehow be related to the radiated power per unit wavelength, which is this curve basically that we've been talking about, the Blackbody spectrum way back here. This curve is the radiated power per unit wavelength, okay? And we have now the energy density in the cavity per unit wavelength, okay? But they should be related, and what we already see is that we've got a problem here, because this energy density per unit wavelength is proportional to 1 over lambda fourth. And what that means is that when lambda gets very small, corresponding to very high frequencies, the ultraviolet, then this is going to diverge. This quantity is going to get very big, and there's no maximum in this function, right? As a function of wavelength, there's no maximum. It just keeps diverging. It just keeps getting bigger as the wavelength gets smaller. And this was called the ultraviolet catastrophe, okay? Because what it said was that if this relationship was correct, was that any object would basically have would have an infinite energy density, particularly at very small wavelengths, very high frequencies. And this basically doesn't agree with the Wien's law, which basically predicts that there is a maximum, and how that maximum depends on temperature, which we discussed. It also doesn't agree with the Stefan-Boltzmann law, okay, which says that the temperature, that the power per unit area is proportional to T to the fourth, okay. And so although this formula leads to a behavior which is consistent with observations at very long wavelengths, it completely disagrees at very short wavelengths. Now let's finish off this derivation by just finding the radiated energy as a function of wavelength. So we have to know how much of this energy actually gets out of the hole.